Welcome everyone. I hope you all have a very smooth travel and the hotel is good. You are settled. Um, First, I would like to give special thanks to the organizer, Yan Matt, Haiyan, and Caleb, and also Nancy. They did all the heavy lifting to do all the preparation to help you guys, especially Nancy, get the uh, gate pass and to be here. And so without their efforts, this is not possible. Then I would like to just give a brief few words about this history of the ISRD. It's essentially a short for in situ studies of rock deformation. This is an NSF-supported research coordinate network. So it is different from a usual research grant. This grant, the design of it is to essentially try to help um, scientists to get together and define or develop new infrastructures or define new research directions. So I would just first talk about what rock deformation is doing. We know the rocky planets like ours on Earth, all right, the dynamic process is really important. And that's left a print on rocks and cause the rock to deform. So essentially, rock deformation is to use physical, chemical, or biological principles and use the mechanical engineering framework to better measure the evolution of the properties of this rock and then to infer the process that lead to the current state of the rock. This becomes really important in many process. For example, NSF published the next decadal research priority, and in that Earth in Time document, they identified 12 areas that will be the research frontiers for the next decade, and that's including plate tectonics, critical elements, earthquakes, volcanoes, etc. So if you look at those process, one of the important thing is that these are dynamic process, and how do you study it? Rock deformation actually would be recording or help us understand what controls the initiation of plate tectonics. What would be the physics of the earthquakes? How about the topographic change and what are the measure or the rate or to predict the future of that? And also with critical elements and the critical minerals, the fluids rock interaction plays a really important role. And how do you study this? So with this understanding of the importance of studying the rock deformation, so researchers in this field essentially use experimental tools to measure rock change under controlled conditions. And that leads to insights and constraints, such as now we understand the physics of earthquake is a stick slip phenomena. So we can use the tribology and all the other experimental studies and the theoretical models to understand and predict what kind of a slip and how these energy dissipate during earthquakes. Another thing that come out of the experimental rock deformation is now the strength of lithosphere, because we know the mountains can stand because the Earth's outer layer can support the weight of the tall mountains, but how much it can actually support at what condition its yield, this also comes out of the experimental rock deformation study. And showing on the left, you see the essentially what we call a Christmas tree diagram. This essentially marks the continental lithosphere and as well as oceanic lithosphere, which is not showing here, the strength profile. That's also in our logo. You see the blue uh, flag. That's actually deciphers the Christmas tree diagram. It's the lithosphere strength. But with the classic rock deformation, one of the problem is you are actually most of time, because the sample is behind a thick metal walls, because you are actually going to have to apply pressure and temperature, and that need to be the sample needs a sample environment, so you cannot see during the deformation how the rock changes. And that's changed when you actually include X-ray and other new beamline technology. Since you are in the next couple days going to mostly look into the high pressure, high temperature rock deformation, where rock is deformed under deeper depth, lower crust, upper mantle depth. I am going to show you a couple examples of the more shallower depths where the pressure temperature is not that high. Showing here is a video that's essentially, I have a rock core. This is a sandstone rock core. What in the core, the white face is quartz. The black face, the blue ones is a pore space. When this rock is now this is a in situ deformation. When this rock is subjected to stress, you can see the stress increases. You start to see as the rock deforms, fracture initiates. It's the correlation of these fractures eventually leads to the breaking of the whole rock, and then the sample loses loading capacity. So the beamline technology here really adds a new dimension to the traditional rock deformation. We no longer just have the initial and end state of the rock and how it changes, but we also have in between the structure changes. So these inspires many more study. Now showing here is one of the experiments we do recently, that we have this curve marks what we call a stress increase. This is a axial stress that's increasing, and this is a time. And where you see is as the stress increase with the X-ray tomography, you start to see the fracture initiate and bifurcate and branch, and lots of fractures, and then how they open, close, and shear, and eventually lead to the failure. This also opens new ways of us to look at rock deformation. Before, because we don't know the in-between state, so often we have to isolate different processes, because if you get very many processes coupled together, then in the end, you're not able to find out which one that's doing what. So you create a problem that you don't know how to really extrapolate and apply. With this, we finally are able to do more complex experiments. This, for example, is one of our group's study done at Jesse Carr's last November. This is what we call a chemofracking experiment. In this experiment, the inside is actually a chemically reactive rock core that's reacting with the fluid. And as this reaction happens, the inside the core is expanding and cracking. With that volume expanding, then they eventually cracks the host rock. Before doing this wouldn't make a lot of sense in that if you don't have the intermediate state, you're not going to be able to separate what are coming from the mechanical, what are coming from the chemical reactions. And now it is essentially opening new windows and new possibilities for us. So recognizing this, that with the imaging now, one thing you can also do is now with the machine learning and AI, you can recognize patterns and you can also compare the time evolution by looking at the digital volume correlation between the deforming rocks, one time step to another. There's a tiny changes. From those changes, you can get its strain tensors, and from there you can start to get its stress tensors. So there's many of the new fronts that's research dedicated to this, and it is a field that's in the exponential growth right now. With that, there's what I call the digital rock physics. Now you can get a high resolution, high fidelity microstructures, and then putting those digital twins of the your rocks and put them under virtual models. You can run flow models, for example, that's showing here. You can run mechanical models that's looking at the stress distribution. And from there, you can actually start to do experiments virtually on digital rocks, which is the digital twin of the real rocks, and then compare to some of the in situ studies, or you can actually do that at conditions that experimentally challenging. And that opens another possibilities. So with all of this, a group of us 7 years ago um, decided that it's time is right for us to actually bring this to a more formalized collaboration. And that's how the in situ rock deformation, in situ study of rock deformation proposal was written in 2019. And these are the steering committee members. You may recognize Yan Bin was here, and there's several other beamline scientists that Mark Rivers. You probably see him as you learn to operate some of the experimental apparatus there. And then Caleb, I want to especially thank Caleb to travel all the way from Ohio to bring instruments and to bring you experimental insight. The ISRD also have an advisory committee. These are people who are not directly involved in the experiment, or they are they basically provide a overview and a feedback to the ISRD activities. And Pamela will give you another, I think, a remote lecture on the stress measurements using the how to analyze the stress data later. So with this in situ study of rock deformation, our goal is to transform traditional rock deformation through innovation and collaboration. And specifically, we organize workshops to get people together and identify knowledge gaps, identify how beamline technology could help to address those issues. we have organized already 5 workshops over the last 6 years, and we have 2 more workshops that will happen in April 26. And we also try to bring the students and the postdoc up to speed for lots of rock deformation groups that a student and postdoc hasn't get a chance to work in the beamline. So our timing wasn't when we got funded in the last quarter of 2019, you know what happens in early 2020, that essentially the COVID shutdown happens. So for a while, we couldn't really bring hands-on users to the beamline and get trained. And then to address that, Haiyan especially leads this shadow beamline user program that's run 2 seasons in 2022 and 2023. And then afterwards, we did 2 other hands-on workshops in 2023 and 2024 on acoustic emission technique and nanotomography technique. And this one is our last one, that when you have high pressure rock deformation, that's happening today. And I really hope you all enjoy it and get useful ideas and inspiration to take home with you. So this is actually the last 4 months of ISRD before it expires in June 2026. I think it's fulfilled what is proposed, the tasks, and we identified the key challenges and the beamline technologies. Now the key is how do we create a sample environment and bring the rock deformation experimentalist to beamline and take advantage of the new technology. This is not the end of ISRD. This is actually the new beginning, because now ISRD is a part of SEAS. With SEAS, the synchrotron Earth and the environmental science, and I think Andy will give you a introduction and tell you what's the facilities there next. What our goal is for the ISRD is to build and expand the infrastructure and especially expand its capacity for rock deformation experiments. From doing this, we can expand the research frontier. But that is why we have the hands-on training, is because with the hardwares, it's not possible to push the research forward without the new generation people like you, the student and postdocs, the early career scientists, to actually get involved and really do transformative work in this field. I will stop here, and hopefully it didn't take too long. Any questions?
Good morning, Professor Zhu. This is Fan from Northwestern. I just have a quick question about your experiment, chemomechanical experiment. What's the, chemical formula within the rock sample? Is it periclase or what?
It's periclase. Periclase with carbonated water.
Carbonated water. And what's the outside layer?
Outside layer in this case is amphibolite.
Amphibolite. Okay. Thank you so much.
The reason we did that was this amphibolite was from an enhanced geothermal testing bed. So they want to know how fracture and fracture pattern associated with volume expansion reactions and stress.
Okay. Yes, it reminds me of a paper from the University of Oslo, the outside layers serpentine, I guess.
Yeah, that's I'm part of that. That is in 2019, 2018, that's we did that. But that is just to test how much of stress you can actually generate to break now we know. And this one is more targeted because our new DOE grant is associated with understanding permeability of hot, dry rocks, and how do you do enhanced geothermal control? Because enhanced geothermal fields actually depends on you fracturing those hot rocks. And but then we cannot measure permeability directly. Now the key is if you see how the fracture was developed, how the fracture network is mapped out, you can actually give some estimate of permeability evolution.
Makes sense. Thank you so much for answering.